Welcome back, everyone, to this month's webinar on using real-time monitoring systems in the semiconductor industry to improve product yield. If you've got any questions during the webinar, please text them using the text field in our webinar platform. My name is Jason Kelly. I am VP of Services at Lighthouse Worldwide Solutions, and I will be presenting today on this topic. Before we get into using monitoring systems in semiconductor applications, let's go over how ICs, the integrated circuits, chips, those magical devices that we have all around us in everyday technology, let's look at how they are produced. The manufacture of semiconductor products is an arduous and complicated process. If we look at a typical wafer fab where integrated circuits are manufactured, the process and the various stages of development of the silicon wafer to a final microchip involves many steps. It is critical that the products are free from contamination, as this contamination, if unmonitored, can have detrimental effects on product yield and product quality. ICs are processed or developed and fabricated on a base silicon wafer. Numerous processes and steps are carried out during the IC development on the silicon wafer. The process of manufacturing semiconductors or integrated circuits typically consists of more than 100 steps. During this process, hundreds of copies of an integrated circuit are formed onto a single wafer. The process generally involves the creation of 8 to 20 patented layers on and into the substrate of the silicon wafer, ultimately forming the complete integrated circuit. This layering process creates electrically active regions in and on the semiconductor wafer surface. So let's start at how the silicon wafer is developed and take a close look at that process. The first step in the semiconductor manufacturing begins with production of a wafer. A thin, round slice of a semiconductor material, usually silicon. In this process, purified polycrystalline silicon created from sand is heated to a molten liquid. A small piece of solid silicon, like a seed, is placed on the molten liquid. And as the seed is slowly pulled from the melt, the liquid cools to form a single crysted ingot. And we can see the ingot here in its completeness, the left image there before the actual wafers are sliced into the wafers themselves. So growing the ingot, the preferred method of ingot growth for the semiconductor industry is the Shostkowski process. First, rocks of pure silicon, that's at 99.99999% pure, are placed in a quartz crucible with a specialized vacuum furnace. This is then heated to about 2,597 Fahrenheit, about 1,425 Celsius, and it melts the silicon. So a small seed crystal mounted in a fixture at the end of a cable is lowered to touch the surface of the melt, and the crucible and the cable holding the seed crystal rotate in the opposite direction, and the seed is slowly drawn away from the melt. This allows growth of the cylindrical crystal ingot to the desired diameter and length. The temperature and pulse speed are carefully monitored and controlled throughout the growth process to maintain crystal quality and avoid unwanted instabilities or defects. Additionally, the crystal can be either P-type or N-type with different electronic properties by adding dopant impurity atoms to the silicon, such as boron or phosphorus. A single wire saw cuts the top and bottom, it's called crown and tail, off the ingot and then cuts it into sections of a manageable length, which are about 500 millimeters. At this point, a multi-wire saw will cut the sections into wafers. The final process steps in preparing the wafers for use in the semiconductors are lapping, polishing, and washing. Layers of material are then applied to the prepared silicon wafer, like a single silicon oxide layer a silicon nitride layer, and a layer of photoresist coating. So the heart of the semiconductor manufacturing is the wafer fabrication facility, where the integrated circuits formed in and on the wafer. Here we see an aerial view of Europe's biggest wafer manufacturing facility located in Ireland. I actually started my career at this facility in 1995, and it wasn't that big, I can tell you. And I was a custom engineer maintaining wafer fabrication equipment. So this is the Intel Ireland site, and it sits on a 360-acre site. And Intel has invested 30 billion since 1989, and is currently investing another 17 billion to this site, the infrastructure, which will double its manufacturing floor space. And this site currently has about 4,900 employees, and at the forefront of the 14 nanometer process technology. So as we see, the sizes are getting smaller and smaller. It's quite a big site. It's like a little city in itself. I just wanted to give you an overview of what a semiconductor fabrication facility actually looks like. So let's take a look at the wafer fabrication process. And did you know that the semiconductor manufacturing process is 1,000 times cleaner than an operating theater? Some food for thought. And Intel Ireland uses about 600 million liters of water per month. And the water's primary use is to rinse the wafers in between processing steps. So it's critical that the water is as pure as possible and free of contaminants that can cause product failure. And you see, particle monitoring is really important. Here we see the life cycle of a wafer. As we just covered how wafers are made prior to the fabrication process, we see here that the process starts with the photolithography stage, where the tiny circuits are masked onto the wafer and developed and then etched, and implantation takes place, followed by stripping and deposition. And this process is repeated as the many IC layers are built up onto the wafer. Here in the masking stage, the photomask, the circuit design, is exposed onto the wafer. It's similar to photography process where images are exposed onto a film. In this case, the wafer is the film, and we are dealing with circuit sizes that are so small the human eye would not be able to detect them. So once the mask pattern is completed, the wafer moves on to the next stage, which is the etching. And etching is the process of removing exposed photoresist, and the wafer is baked to harden the photoresist pattern. A plasma gas is generated inside a chamber under vacuum, and the wafer is placed into this chamber using robotic arms. As I said, this chamber is under vacuum, and this plasma gas rotates by electromagnetic forces and scrubs the area not covered by the hardened photoresist, and those areas are then etched away. The gas used for the plasma is chlorine. It can be used as other gases. From my experience, we use chlorine at Intel, and that plasma generates a pinkish color. So I spent 3 years working on the metal etch tools, and we were always under pressure to keep the tools in service and up and running, as there were endless wafers to process. And it's quite a interesting place to be in the metal etch department anyway. I learned quite a lot on the whole process, and keeping those tools up and running was a pretty hard task as well. The doping process is the introduction of impurities into the semiconductor crystal wafer to deliberately change its conductivity due to deficiency or excess of electrons. This process creates positive and negative areas on the wafer. Since silicon has 4 electrons in its outer orbital that can form perfect covalent bonds with 4 other atoms, the element can create a framework for crystal structures. Although this crystalline structure looks metallic, silicon crystals aren't metals. For this reason, only a tiny amount of electricity flows through it. However, all this can be dramatically changed by forming P and N-type semiconductors through the process of doping silicon. The doping process involves the intentional introduction of impurities into an intrinsic semiconductor. So a chemical reaction that occurs during the process enables impurities to form ionic bonds with the silicon atoms in its crystal. Thermal oxidation is a process done to grow a layer of an oxide on the surface of a silicon wafer at elevated temperatures to form silicon dioxide. The deposition process can build up layers within the IC structure. These layers will themselves have multiple processes where the IC circuitry is built up. So the process we covered: masking, etching, doping, repeated until the front end layers are completed on the wafer. So we should look more at deposition, passivation, and electrical testing in the next few slides. Following completion of the front end process we just went over, the individual devices are interconnected using a series of metal depositions and patterning steps of dielectric films, which are electrical insulators. The ICs are interconnected this way with up to 15 layers. Here we see an image on the right side of the slide with these layers visible under an electronic microscope magnification. They kind of look like little cities, if you can see there. And you can just get an idea of the levels that we're dealing with here with these wafers and the integrated circuits. And you can imagine, like, contamination control is of paramount importance during these stages. And we're looking at sizes that are in the sub-micron, sub-nanometer size range, getting down to less than, some stages less than 10 nanometers. So it's critically important that we keep this wafer and this process free from particles from the operators, particles from the clean room itself. We can get to understand and appreciate the sizes here that we're dealing with in the semiconductor industry. Here we see more examples of the sizes we're dealing with. Line widths in today's modern ICs are in a nanometer range. You can imagine the need to continuously monitor for contamination, as these line widths are so narrow. Tiny particles that we can't even see can cause IC failure and be detrimental to product yield. So you get to understand the need for particle monitoring, especially when you are looking at these tiny circuits. In some instances, the sizes of atoms, really, really small. It's a small world. Passivation layers normally protect the active semiconductor surface from the surrounding environment. And the passivation is also used to prevent corrosion and to protect the IC circuit itself. And it's basically just a process of enabling the bond wires and everything to be clearly covered, and they also still exposed so they can be later on connected up during the connection stages in the assembly. Next, we move on to the electrical testing. In situ, automated testing checks the functionality of each chip on the wafer. Chips that do not pass are marked for rejection. So only the viable chips are used and moved on to the next stage. There are many forms of the electrical testing. Here we see an automated version using testing electrical properties on the wafer. Individual circuits on the wafer are also tested and marked good or bad. After the electrical testing, the individual ICs are cut out of the wafer. They're visually inspected and then assembled into a package which has contact leads for the chip. Here we see interconnecting wires. A wire bonding machine attaches these wires. Some are no less than the width of a human hair or even less. Once the wiring is complete, the chip is encapsulated within a plastic coating and tested again prior to delivery to the end user. In military application, the chip is encapsulated in a ceramic package for extra security. So now we have got a good overview of the journey of a silicon wafer. And it takes from the development to the assembly stage. And we see there are many processes involved. Based on the IC layers involved, the process can take from anywhere up to 8 weeks to complete the journey. All these processes have a level of risk involved in terms of contamination. Determination of what and where to monitor for contamination can be daunting. By understanding the wafer fabrication process and following a well-developed risk assessment, what to monitor and where to monitor becomes more easier to identify. And risk assessments are widely used in the pharmaceutical industry. And this presentation doesn't go into that detail, but it will cover the basics of a risk assessment. And, I'm seeing more and more semiconductor companies going down this route because they're starting to fully understand that meaningful data is better data. The risk assessment is based on knowledge of the process and understanding the weak points of that system. It's recommended that senior management take on this responsibility and assign a team of process and cleanroom experts to develop the risk assessment. The team should collectively be able to identify locations and processes where contamination of product or process is a possibility and to monitor those locations. For example, before the thermal oxidation or deposition process, chemicals are used in the pre-cleaning of the wafer. These chemicals would need to be routinely tested for particulate contamination. You do not want to introduce contamination into the process. So using liquid particle counters to monitor the cleaning chemicals really makes sense, especially the ultra clean water as well, used for the cleaning processes. So during the etching processes, gases are introduced, and these gases also need some routine monitoring to ensure that they are not a source of contamination. Gas suppliers are required to provide certificates that indicate the purity of the gases. However, in a risk assessment, in-house monitoring of batches of gases should be undertaken to ensure the quality of the gas remains intact. So anything that you're introducing into the clean room, it is highly recommended that you monitor the cleanliness of that, if it's a gas or the air itself, and anywhere around the processes. Even the liquids that are used as well, as I mentioned, highly important. So line yield and defect density are two of the most closely guarded secrets in the semiconductor industry. Line yield refers to the number of good wafers produced without being scrapped, and in general measures the effectiveness of material handling, process control, and labor. Die yield refers to the number of good die that pass wafer probe testing from wafers that reach that part of the process. It's intended to prevent bad die from being assembled into packages that are often extremely expensive and measures the effectiveness of process control, design margins, and particulate control. So continuous device miniaturization in the semiconductor industry and the trend to go larger and larger with die sizes means that particulate contamination has an ever-increasing impact on yields. Today, over 80% of yield losses of VLSI chips manufactured in volume can be attributed to random defects in contamination. From the risk assessment, the persons who undertake the assessment should have the experience and process knowledge to identify the weak points in the wafer fabrication process. If expertise is not available internally, then external consultants can help with the risk assessment. In the examples above, we see there are 3 applications where particle counters can be used to monitor, like number 1 is liquids, number 2 gases, and 3 is the clean room environment itself. With the advances in technology, real-time monitoring systems, or RTMS, that incorporate liquid, gas, and environmental monitoring are ideal for such applications because they give you the data in real time of different processes and different areas of the clean rooms, and also the introduction of clean water or gases and the environment itself where the wafers are processed. So real-time monitoring enables faster decisions to be made. Consider the cost of a batch of wafers nearing the end of the process. After these 8 weeks, that cassette of wafers could be worth, hundreds of thousands of dollars or more, and there could be 100 cassettes undergoing processing. What if one of the tools or the environment was compromised? The time it can take to realize such an issue and the time a decision is made could impact greatly on product yield. The real-time monitoring systems, that time to make a decision, with real-time monitoring systems, you do have that time to make the decision to halt processing and investigate the issues. And that could literally save hundreds of thousands of dollars and improve product yield once these issues are dealt with. And sometimes you can see these issues happening before the process is affected, and that gives you time to react. So by using this technology, informed decisions can be made faster and also more efficiently. Which departments need to monitor for particle contamination, and what type of monitoring is recommended? Well, so each step in the process will have unique monitoring requirements. As we have outlined, the wafer fabrication is an extensive process which can take up to 8 weeks based on the multiple layers and transistor load of the circuitry design. So Table 1 highlights the departments that should consider using particle counters: remote and portable liquid and air particle counter sensors can be integrated into the real-time monitoring system. And all departments can access the real-time monitoring system to view the whole facility or just to focus on their specific area. The real-time monitoring system can also monitor door sensors, temperature, humidity, room pressures, and even airborne molecular contamination. Monitoring devices can be connected to the real-time monitoring system as well. So Table 1 identifies the different processes and the level of monitoring that we just looked at here. We can quickly just go back over that. The facility department, quality assurance, photolithography, thin film, etch, diffusion, implant, inspection, they all have different needs. And you can see to the right of that table all of the different types of monitoring that you can apply to these areas. So it's a good guideline to give you a head start of what to monitor in which location, in which department. Now, as I said, this table identifies different levels of monitoring. So the facility department typically undertakes site monitoring activities in relation to cleanroom standards. ISO 14644 is the current cleanroom standard. This is one came out in 2015. It's the current cleanroom standard, and it's followed worldwide in the cleanroom industry. Each room is classified based on the level of contamination observed in a cubic meter of air sampled. Table 2 here, as we're looking at, is the current ISO 14644 Part 1 classification table. And it specifies classes of air cleanliness in terms of the number of particles expressed as a concentration in air volume. It also specifies the standard method of testing to determine cleanliness classes, including selection of sampling locations based on the area of the room to be sampled. And we see they go from an ISO class number from 9 to 1, 9 being the dirtiest and ISO 1 being the cleanest. So there's a difference between cleanroom certification and routine monitoring. So portable airborne particle counters are typically used to certify the cleanroom based on the ISO 14644 table, and the frequency is based on ISO 14644 Part 2. And from this table, each ISO class number from 1 to 9 represents the level of cleanliness based on particle concentrations of the sample of 1 cubic meter. So semiconductor cleanrooms are typically from ISO 1 to ISO 5 based on the risk of contamination to the process and the type of processes that are being carried out. So the higher sensitive processes are typically lower ISO class numbers, with ISO 1 being the cleanest environment with only 10 particles allowed per cubic meter of sampling of a size of 0.1 microns. So that's extremely clean area. So with your real-time monitoring system, in the example here, the real-time monitoring system immediately picked up an event in one of the environments where wafers were being scanned for surface contamination. So DMA tools are used in the process to systematically monitor wafers from a batch during the process to determine wafer condition during the process. If the surrounding environment did not have a particle counter monitoring that environment, the issue could have been a major one. So the technician would have reported the wafers have high concentration and would be looking at previous processes to identify the failure. That would have been pretty futile, as the origin of contamination was coming from the room environment where the DMA tool was located. So without this knowledge, without having this real-time monitoring in this area, the root cause may have taken a long time to address. So how much product would have been lost here? How much downtime would have been to conduct the investigations? In this issue, the location was observed immediately, and the root cause of the contamination was found to be a puncture in the HEPA filtration system, and the issue was corrected within an hour. So by having that knowledge on the locations as to where the issue is happening, you can lock in on that location and figure out what's causing that high contamination. You can see here with the diagram, you have a major shift in the particle counts, which was immediately identified using the real-time monitoring system. Here in this example, we see that humidity levels were accidentally triggered to increase. Since the HVAC system is unable to monitor itself, the independent temperature and relative humidity sensors connected to the real-time monitoring system picked up that the shift in humidity levels and notified the facility manager who made the corrections quickly. So imagine if this event went on for several hours or a couple of days, cleanroom operators would notice their comfort levels have decreased due to the higher humidity and the temperatures, and the higher humidity would influence electrostatic occurrences, and the operators would actually be shedding more particles as well. So that is something that you do not need to have in a wafer fabrication process. So you need to have these tight controls of the HVAC. And with a real-time monitoring system, the system was able to correct itself and identify the problem, and the HVAC was reset back to the correct levels. In this example here, the real-time monitoring system captured a high particle concentration event. The ISO 7 room and the ISO 5 room door did not fully close due to pneumatic failure of the door arm. So the ISO 5 room started to get high particle counts ingress from the ISO 7 room, and the facility manager was able to manually shut the door and activate a service call for the cleanroom door company to come out and repair the faulty actuator. So folks, these are just a few examples of the benefits of a real-time monitoring system. The real-time monitoring system is the watchdog for the wafer fabrication cleanroom. Depending on the type and number of sensors connected, that watchdog can be a very valuable tool. In these three examples, time was a major factor. The longer the event went by without notice, the higher the probability of contamination and yield losses. So let's look at some future or further benefits of using a real-time monitoring system. You can view conditions of all cleanroom levels in real time using maps. Warning and catastrophic events are triggered. It provides visual, audible, electronic, or pager notification to engineers and operators. It automates sensor data collection, analyzes and measures cleanroom performance, highlights contamination problems, correlates problems to other parameters and yields, identifies trends and provides early warnings, reduces failure analysis time, assists in post-mortem analysis of various locations, aids in the efficiency of shutdowns and restarts, shows your customers that you're proactively managing the manufacturing environment. Here we see some applications of airborne particle counters used in a wafer fabrication facility. Cleanroom certification, you can use the portables. Daily routine testing to comply with ISO 14644 Part 1, again with portable units. You can have continuous monitoring of general locations, the aisles, the chases, the gowning areas, high traffic areas where people are going to be, and also the continuous monitoring of critical process locations, stockers, tool locks, mini environments, inside process tools, stage for stepper or scanners, wafer inspection locations, photomask, stocker inspections, garment testing, monitoring of tools using chemical solutions and liquids, monitoring of DI water and ultra clean water loops used in the process, and the monitoring of gas introduced into the processes. So you see there's a multiple area and locations for monitoring in the semiconductor industry. So now advances of we've got some new advances in portable particle counting technology. So let's have an overview of these counters and the different systems that you can actually implement in the monitoring. So technology allows for a digital system where data integrity is intact, reporting is more efficient, and reporting data is faster and more reliable, and eliminates human entry errors and does away with the need for paper records. The Apex Z is a great unit because you're able to have a paperless system which will connect into a real-time monitoring system also. And the advantages of using the latest digital technology has many benefits and offers the end user a more enhanced system for notification and record keeping, and also the trending of data. And it'll eliminate paper from the cleanroom altogether. So you have a better data integrity with less risk of human error in transcribing that data, and an overall smoother system by using the latest technology available. For applications where size matters, this portable unit here, the 1100 LD, will go down to 0.1 microns, and it has many semiconductor measuring applications covered. The unit can follow ISO 14644 Part 1 for cleanroom certification purposes, where 0.1 micron needs to be reported. And the unit can also be connected to manifold systems and also used to monitor gases. So it's quite a versatile unit here. And next up, we talked about connecting to manifold systems. So in areas where real-time monitoring is not always necessary, based on the process risk, the use of a manifold system may be considered. Manifold systems are a form of sequential monitoring. Most particle counters and monitoring systems update at a frequency of once per minute because they're pulling data from multiple particle counters. Here we have one particle counter connected to a manifold, and this manifold could have up to 30 locations. So if you're updating every minute, you're going to hit every location every 30 minutes. And that, based on your risk assessment, that may be adequate for your process, that every 30 minutes you see the particle counts in those locations. So in some processes, that level of monitoring frequency is acceptable. So choosing the monitoring frequency and the type of monitoring equipment should be determined, as I said, using the risk assessment. In real-time monitoring systems, the monitoring is done 24/7, typically using remote particle counters, and the real-time monitoring system is used as a process diagnostic tool to ensure critical locations and tool sets are not indicating high levels of particle counts. As we've seen, these high levels can impact on product yield, and the real-time monitoring system early warning detection is a very valuable tool in enabling fast decisions to be made. Another good tool to have is a handheld particle counters. And handheld particle counters are a great tool for spot checks. So if these areas that you're monitoring, you have some high particle concentrations, you can go into the clean room and try and pinpoint the location or the source of the contamination. And it's a nice, easy, quick test that you can go in and just grab a handheld unit and start to do some monitoring and try and locate the source of the contamination, whether it's a filter that's causing some issues, or if it's a tool, or if it's just some people in general who are not following proper protocol. So for real-time monitoring, remote particle counters, as I mentioned, are used. So because of the relatively small footprint, these remote particle counters can be located closer to points of interest along the wafer fabrication process. And as we previously discussed, the location should be determined on a risk-based assessment. By studying your process closely, you can identify points of interest to monitor continuously. And these locations will yield the best data from the process, and it can be used quickly to alert users of situations where contamination may pose a risk to product yield and quality. Water systems in the semiconductor industry are of major importance to the wafer fabrication process. For example, 1,000 gallons is required to produce a single wafer. So these ultra-pure water systems need to be monitored, and the Vertex 50 with a size resolution of 50 nanometers has a small footprint, and it's easy to locate next to critical systems. So your water system is key to high yield and high product quality. When you start to monitor at sub 100 nanometer, the resolution of the liquid counter is extremely important. And some liquid counters at this level do not have, and they kind of have some issues with high background noise, and therefore the data may not be as accurate as it can be. With the Vertex 50, the accuracy down to 50 nanometers is the best available, and we're able to prove that and validate that. And if you need to ensure the quality of your water systems, you definitely need to have good resolution. And if your water systems are contaminated, then the wafer fabrication process will be halted, and the yield of your product will go down. So it's really important you monitor these processes with water, with liquid particle counters. Here we see some remote liquid particle counters, and they can be used in conjunction with the Vertex 50 to monitor different critical locations on the water system. For example, along filtration points and output points. With small footprints, these sensors can be easily installed and can be added to the real-time monitoring system. So you can continuously monitor your water as it comes into the facility. Here we have an example of an ultra-pure water system, and the locations to monitor based on risk assessment to get the most meaningful data. As you can see, the water system has many stages with pre-filtration and final filtration. In this example, we see the water system is continuously monitored. Here we see the data and the resolution performance of the sensors with the data pulses indicated well outside the noise level for more accurate data. So data integrity and the accuracy is paramount. And so it's important for end users because they're making critical decisions which may affect product yield and quality. You definitely want to make sure that your water systems are as clean as possible, or else otherwise you're going to have detrimental effects further on down the processes. And by the time you realize that, if you're not monitoring it, you could be millions of dollars into the product, and you may have to scrap all of that because of the risks of contamination. Finally, for applications where HEPA and OPA filters need to be validated, then the ScanAir Pro is a valuable piece of equipment and needed in every facility. Air filter integrity is crucial for the cleanroom operations and for control of contamination inside the cleanroom. ISO 14644 Part 3 allows for the use of airborne particle counters to conduct filter validation activities and verify filter integrity. This method uses reference particles instead of oils. Oil aerosols have been shown to clog up filters, and they are actually, the ones they're actually testing. So there's one major advantage, as well as the higher resolution of a particle counter over a traditional photometer, which collects concentrations of data instead of sizing data. So with the particle counters with the ScanAir Pro, you've got a system that's already there that will scan the filter face and give you more accuracy, and it will give you the actual sizing, not just the concentration level, so you get more resolution. And you're also using references instead of oils, so you're not going to clog up your filters with the process. Okay, we did cover a lot of ground, so what have we learned? So in summary, by establishing effective monitoring systems based on science and knowledge, you can empower your facility and mitigate against product yield losses. Real-time monitoring systems offer live data, and production managers, quality managers, facility engineers, and line managers can be notified in real time if events will have a critical impact. The wafer fabrication process is very labor and machine intensive, and with up to 100 processes. There are many areas to monitor, and this webinar outlines the best options and applications to monitor and identifies the right monitoring equipment. So as environmental contamination can adversely affect product yield, monitoring these environmental conditions is mission critical, as well as the gases and the water systems and everything else that you introduce into the process. So, a single excursion can cost hundreds of thousands of dollars in product loss. So with real-time monitoring systems and redundant data collection, your data will be automatically recorded to two databases simultaneously. So you've always got your data. And, with mirrored databases, if the main computer fails, the secondary will automatically take over data collection. And it provides you with uninterrupted data collections and alarming of out of specification conditions. So the redundancy of the real-time monitoring system is critical. In the example shown, using a real-time monitoring system and the events alarmed, you can see that the real-time monitoring system is a valuable process. You remember we looked at the door switch, the door opening, the humidity, and the failure of the HVAC filter. So they all had detrimental effects, but the real-time monitoring system picked up those effects pretty quickly and notified the right people. So the real-time monitoring system is a valuable process monitoring tool. And as I said, this tool enables faster decisions to be made, and it can, in some cases, locate root causes of contamination. So time is money in this industry, and downtime results in harmful and expensive product yield losses. So if you're looking to implement a real-time monitoring system, then it is recommended to form an internal team of subject matter experts or hire external consultants and engage with a vendor that understands your process and can assist in the project. So developing a risk assessment is the first step, and a well-developed risk assessment will definitely pay dividends with the installation of a real-time monitoring system. So I'd say use a quality vendor with quality products and a proven track record in the semiconductor industry. Let's move on to our question and answer stage. So here we have a good question. So how many semiconductor facilities are using a risk assessment for determination of sample locations? So risk assessments have previously been widely used in the pharmaceutical industry based on the GMP regulation and the fact that end users see the advantages of risk assessments on their processes. I'm starting to see an uptake in the semiconductor industry on the use of risk assessments. So process engineers and facility managers are starting to use them and locate monitoring points that will report more operational significant data back. And here at Lighthouse, we have specialists that can also come on site and work with your team to conduct risk assessments and identify the best sample locations. At the end of the day, it's all about the data integrity, and the quality of that data for your facility. Question number 2, how long would it take to install a real-time monitoring system? So, good question. I would make allowances for such a project to take about 3 to 9 months, or it could even be longer. And that's depending on the number of sample locations and the size of the facility. So the stages of implementation consist of identifying the needs and the locations, type of sensors, type of networking, the system design, and the managing of the project off-site and on-site. So there are many steps involved in installing the real-time monitoring system. You know, the planning stages themselves may actually take longer than the actual physical installation. And then there is some commissioning and the training of the team so that they're able to use the system. So anywhere between 3 and 9 months is more of a realistic expectation. And also there's the time needed to develop the risk assessment as well. So that could be anywhere between 2 and 3 months, depending on the teams, how much time they have to dedicate and how much knowledge they have as well. So a lot of our projects do take this long. And then we've also got some lead times as well to deal with getting the products and scheduling the team to go do the installations. And sometimes customers may have shutdowns, sometimes they may not. We may have to work around the non-shutdown periods, which makes it a little bit more tricky with the installations, but we always get there in the end. So yeah, I would allow anywhere up to 9 months or even maybe up to a year, depending on the level and the size of the project. Question 3, how was the accuracy of the Vertex 50 validated? Another great question. We actually have dedicated a whole paper on this topic, and that can also be found on our Knowledge Center from our main website. So the calibration process of the Vertex 50 runs through the range of particle channels and verifies the sizing accuracy, the count accuracy, the sensitivity, zero count, and false count validation. This process introduces traceable reference particles into each channel. The traceable particle size is introduced at the first stage, and in stage 2, particle-free water is introduced through 2 post-CLRW filtration stages. In the third stage, the traceable particles are introduced into the dilution system, and the diluted particles are then carefully controlled based on a dilution ratio. So the concentration is known. Each channel is tested individually against a reference unit. The counting efficiency and the range of the Vertex 50, the one under test, and the reference standards are also known. So in stage 4, the unit under test and the reference standard are compared together. The ratio of counts are calculated to verify count accuracy. All channels thresholds are adjusted on the instrument under test until counts are within plus or minus 5% of the reference standard. And zero counts and dark noise must be validated, so there's no false counts introduced into the system here. Is a bit of an idea of the different stages that we've set up, and then we've also got the reference unit and the unit being tested compared against each other. So it's quite a process. Question 4, what is an ultra-pure water system? So ultra-pure water systems, they clean the water, keeping it particle-free, so it can be used to clean and etch in manufacturing, especially in the semiconductor industry. The pharmaceutical industry also uses ultra-clean water too. And the ultra-clean water is used to clean the wafer in between the processes of wafer fabrication. Industries that use ultra-pure water use a lot of it. For instance, to process a single wafer, I said over 1,000 gallons of water is needed. So it's important to understand what an ultra-pure water system does, how to maintain it, and how to make the most of it to keep your system working and prevent yield loss. A liquid particle count will monitor the ultra-pure water you're using in your setting to make sure it's truly as clean as you need it to be, and to maintain the standards you hold to your ultra-pure water system as well. So there are about 3 stages in an ultra-pure water system: the pre-treatment, the primary, and the polishing. In the pre-treatment phase, you get the basic purified water. Depending on your system, you may use two-pass reverse osmosis, demineralization and reverse osmosis, or high efficiency reverse osmosis. Additionally, the water is cleaned off of any large debris, easily caught in a filter. This phase also might incorporate activated carbon or sodium bisulfite to dechlorinate the water as well. Next, the water enters the primary treatment phase. During this phase, the water is passed under ultraviolet light as well as undergone electrodeionization or a mixed bed ion or to achieve maximum demineralization. To finish this step, you might use dissolved oxygen removal using membrane or vacuum degasification. Finally, the last and most important but sometimes expensive step is creating ultra-pure water. In this stage, ultraviolet light and heat exchange is used to control the temperature in the ultra-pure water supply. The non-regenerable ion exchange coupled with membrane degasification and ultrafiltration are used to truly filter the water down to the necessary particle levels. After these three stages, the ultra-pure water is ready to be utilized in your system, as we see the output stage here. Quite a nice little graph that we have here. Okay, that's it for the questions. But if I've missed anything, please, as I said, type in your questions and I'll get back to you within a day or two. So before I go, I do highly recommend you get onto our Knowledge Center. You'll find much more information on various contamination control topics. And it's the most advanced library of information you'll find in one location on the web. If you ever need further information, please drop me a line. My email, jason.k@golighthouse.com. You can just find me on LinkedIn. You can email me. Yep, I like to get those emails and get back to you. And I do recommend that you do go onto the Knowledge Center. There you'll find and you'll be able to download a paper based on today's webinar. If you do a search under semiconductor, you will find today's paper and also other topics in relation to particle counting in the semiconductor applications, as well as that paper on the validation of the Vertex 50 I just went over in one of those questions. So create yourself an account and get onto our Knowledge Center, folks. So that's it for today. I do hope you found this webinar of help. Please let me know how you feel, maybe some feedback, and if there are any other topics that you would like me to cover on contamination control, please let me know. Again, my email is jasonk@golighthouse.com. And I hope to see you in the near future. Take care, folks, and be safe out there.